Assalamualaikum and hello everyone, my name is Razia Rahim. Today me and my groupmate going to present to you the last chapter of PHY210, which is the ideal gas law and the kinetic theory of gas. So as you can see on the slide right now, this is all my group members. The first presenter will be me, Razia Rahim. The second presenter will be Sharifah Shakirah binti Aluwi. And the last presenter, which will be Ummi Khairiyah binti Taufik. So today's video is going to be in 3 parts. So the first part will be what is ideal gas law and the equation used. The second part will be the application of ideal gas law. And the third part will be kinetic theory and the equation used. So we're going to start today's video with the first part. So what is ideal gas law? So ideal gas law is a study that helps us model and predict the behavior of real gases. This term refers to a hypothetical gas composed of molecules which follow these two rules. So the first rule is ideal gas do not attract or repel each other. The only interaction that in gas molecule is the elastic collision that came from impact with each other and with the walls of the container. So the second rule would be ideal gas molecules themselves take up no volume. Gas normally takes up volume from expanding into the light region of space, but ideal gas molecules are approximated have no volume in and of themselves. So this is the ideal gas concept. So this equation shows the relationship between temperature, pressure and volume for gases. This concept actually came from the Charles law, identified proportionality volume occupied by gas and temperature at fixed pressure. The Boyle's law, which identified the inverse proportionality of pressure and volume in a constant temperature, and Gray-Lussac's law identified the direct proportionality of pressure and temperature at a constant volume. So this is the example. So when you pour air into an initially deflated tire, its volume first will increase in direct proportion to the amount of air injected without increasing the tire pressure. Once it's expanded to nearly full size, the wall will expand, but if we continue to form it, the pressure will increase and will further increase as the car is driven. So this is the ideal gas equation. So we have PV equals to NKT. So P equals to absolute pressure of the gas, B equals to volume occupied, N is the number of atoms or molecules in the gas, T is the absolute temperature, and K is the Boltzmann constant, which is 1.38 times 10 to the power of negative 23. So that is all for the first part of today's video. I'm going to pass the presentation to our second presenter, which is Sharifah Shakirah. Thank you.
Assalamualaikum, I'm Sharifah Shakirah binti Syed Aluwi. So today I'm going to explain about application of ideal gas law. First is ideal gas law in planes and buildings. Commercial buildings are one environment where ideal gas law are very beneficial. This is because in any commercial building where air ventilation is insufficient to maintain a balance between the amount of oxygen and carbon dioxide in the air, ventilation units must be installed. The amount of ventilation required by a building is determined by the number of people present and their level of activity. For example, the building with high levels of human activity require more ventilation rather than the building with lower levels of human activity or fewer people moving around. Ideal gas law also apply in enclosed space such as planes, where a proper pressure balance between the inside and outside air is required. Information on the average pressure in the cabin and the surrounding atmosphere, as well as the percentage of oxygen in the atmosphere and the ideal gas law can be used to calculate how much oxygen is needed to maintain the proper balance between the air inside and outside the cabin and keep it fresh. That is why ideal gas law is very important, is very beneficial in planes and buildings application. Second is ideal gas law in hot air balloon. According to the ideal gas law, when the air inside the balloon being heated with the burner, its density decreases, resulting in the air density inside the balloon being less than the density of cool air outside. So the cool air outside causes the balloon to rise upwards by exerting an upward buoyant force on it. Same goes when the density inside the balloon being more than the density of of cold air outside, the balloon will go down. So in this case, we can see that there is a buoyant force acts on hot air balloon. That is mean the buoyant force is not just exerted on the thin fluid on the water, it is also applied on the thin fluid on the air. Third is ideal gas law in airbags. The working mechanisms of airbags are determined by ideal gas law. When airbags deploy, they quickly fill the right gases to inflate and then properly inflate as the vehicle crashes. Nitrogen gas is used to fill airbags when they inflate. The nitrogen gas is created by reacting potassium nitrate with another substance. This reaction neutralizes the potassium, which produces enough gas so that the airbag is inflated but not overfilled. Most vehicles have airbags that are located in front of the driver's seats and passenger seats, which protect occupants in the event of a hit-on crash. That is mean whenever we involve in the accident, the airbags will be activated. Some vehicles also have airbags along the sides of the passenger seats, which are called side airbags. These airbags are usually found above the windows and help protect the heads of passengers in the event of a collision.
For the last part of this topic is kinetic theory of gas. Kinetic theory of gas is a theory on a simplified molecular or particle description of a gas that can be derived from the many properties of gases. These are the 5 assumptions of kinetic model gas. First, a gas is made up of molecules separated by a distances that much more larger than the size of molecules. The volume filled by the gas molecule is insignificant in comparison to the volume of gas itself. Second, intermolecular forces of attraction between the gas particles does not exist. Third, the molecules are always moving at random motion. Fourth, when the two molecules are collide with each other, they tend to change their direction and kinetic energy, but overall kinetic energy are conserved. This is due to the collision between gas are completely elastic. Lastly, the average kinetic energy is directly proportional to the absolute temperature. The molecule's velocity and kinetic energy will widely range, and some may have zero velocity at certain time. Then the average kinetic energy for all gases at given temperature are remain the same. As the average translational kinetic energy of an ideal gas is directly proportional to its absolute temperature according to kinetic molecular energy, the last expression can be written as Ke equal to 1 over 2 mv squared, which is equal to 3 over 2 kT. Ke equal to the kinetic energy of molecule, m indicates mass of the molecule, V indicates the magnitude of velocity of molecules. The expressions are derived from first, the pressure can be explained in microscopic phenomena in terms of kinetic molecular theory. In this case, a gas molecule were in the container with length L. This can be assumed that the gas molecule only move horizontally in one direction, so it can be seen that the gas particles were colliding elastically with the wall of box. Then, when examining the n dimension, the momentum of this collision is given by P equal to mv or P equal to mvx. The overall change in momentum for this collision is given by mvx minus m times negative x, which is equal to 2mvx. Third, the total time between collision of molecule with the wall is L over Vx, and the frequency of collision with the wall of box per unit time can be calculated as Vx equal to 2L. The change in momentum per unit time now is the 2mvx times V over Vx over 2L, which is equal to mvx over L. Last, then the force exerted by an object is calculated by solving the momentum per unit of time, which is F equal to ma or P equal P over time, which is also equal to F over mv squared. That can be calculated the pressure exerted by a molecular collision where area is defined as the area of the box wall, A equal to L squared. So the equation will be P equal to F over A, and then P equal to mvx squared over L times L squared. So the following equation that can be stated in terms of the pressure associated with a number of molecular condition is P equal to n mvx squared over V. Using the mean square velocity for the 3-dimension and a large value of n, formula can be used for the movement in the x, y, and z direction. The expression is written as below, which is P equal to 1 over 3 times n mv squared over V. Thus, in terms of atomic motion, the expression shows the pressure of a microscopic quantity. Then it can be rewritten as PV equal to 2 over 3n times 1 over 2 mv squared. And lastly, PV equal to nkt, which can be written as Ke equal to 1 over 2 mv squared, also equal to 3 over 2 kt. Lastly, the average speed of particle is proportional to their absolute temperature according to this equation. To put in another way, when their temperature rises, the speed also rises as well as the energy. Unfortunately, it is impossible to determine the speed of each gas molecule. As a result, the root mean squared speed of gases is used to define them, which we written as Vrms equal to square root V squared, which can be divided with two equations. V Rms equal to 3 kt over m square root, and also Vrms equal to square root 3 rt over m.